So in today's class, we are going to talk about forces and moments. Now, what is the deal with forces and moments? So please understand, these are the same 12 equations that we talked about in last class. But the only difference is these equations are written in Euler angles. We have 6 equations that talk about the kinematics of the UAV, and we have 6 equations that talk about the dynamics of the UAV. Now, if you look at the right hand side of this equation, we have Fx, Fy, and Fz. These are the forces in x direction, y direction, and z direction in the body coordinate system. And I have the moment Lmn, which is the moment about x-axis, moment about y-axis, and moment about z-axis. This entire chapter is devoted to how do we find out Fx, Fy, Fz, and how do we find out L, M, and N. Now, if you think about sort of a broader perspective, an aircraft has its self weight, the force because of gravity. It's going to have some aerodynamic forces because of the lift and drag. It will also have some propulsion forces because of the thrust. And because of the deflection of the control surfaces, we are going to get the torques L, M, and N. In this chapter, we are going to talk about what are the forces, what are the moment, and how do they affect the longitudinal dynamics of the aircraft and the lateral dynamics of the aircraft. And the reason we need to understand the longitudinal dynamics, because in the next chapter, we have to design a control stabilizing system that will stabilize the aircraft in the longitudinal dynamics and then stabilize the aircraft in the lateral position. So we have to understand what are the forces acting on an aircraft, and so that we can control them. Please understand the equations that are shown over here. Those equations are expressed in Euler angles. They are not in quaternions. The project that you have, in that project, you have to solve the equations in quaternions. But these equations, you can see explicitly state phi, theta, and psi. So these are Euler angles. Now, the total forces, if you think about all the forces which are acting on an aircraft, there are 3 types of forces. One is the force because of the gravity Fg. Second is the aerodynamic force. And the last one is the propulsion force. The propulsion could be because of the props, or it could be because of the jet. So you must have seen the planes that have props in the front, or you must have seen the planes that have jet engines, 1, 2, or 3. So the Fp, which is the thrust force, would be given by a prop, or it could be given by a jet. Now, there are external moments. Those moments are because of the aerodynamic moment, and these moments could be because of the propulsion moment. So, first and foremost, let's identify the gravitational force. If you look at the force because of gravity, gravity is always going to act in the downward direction. So weight of the aircraft will always be going down. So if you have the gravitational force which is acting in the z direction, what we need to do is, at the end of the day, I want you to understand all our equations, the 12 equations that I showed you, are expressed in the body coordinate frame, which means what I need to do is the gravitational force which is in the vehicle frame that needs to be transferred to the body frame. So what I have is I have this rotational transformation. Please understand and look at this. This is the rotation matrix. This rotation matrix is body RV. So this force, which is the force because of gravity, is in the vehicle frame. Vehicle frame. And I am multiplying this force because of the gravity by this transformation, so that after multiplication, the forces I get, these forces are in body frame. Everyone understood this? And the reason I want everything in the body frame is because my 12 equations of motion are expressed in the body coordinate frame. Everyone understood this? Now, if you want to express the equation in quaternions, the direction cosine matrix, that roll pitch yaw matrix that I have shown over here, can be expressed in its equivalent quaternion rotation. Once again, a quick recap. We have the first frame is the inertial frame. Once you translate the inertial frame to the center of gravity of the aircraft, you have the vehicle frame. Vehicle frame and inertial frame have pure translation relationship, no rotation. From vehicle 1, you have vehicle 1, then you have vehicle 2, and then finally you have the body frame. Then what you have is stability frame, and then you have the wind frame. Remember all these frames? So right now, gravitational force is in vehicle frame because it is acting at the CG of the aircraft, vertically down. So that's why that gravitational force is positive, because it is aligned with the downward pointing K vector. And then once you multiply this by direction cosine matrix, you have the component of gravity in the body coordinate frame. Everyone understood this? If you replace this direction cosine matrix in its equivalent Newtonian representation, this is exactly the same matrix, BRV. The only thing is, this is expressed in terms of Newtonians. So you will get the component of force that is expressed in the Newtonians. Everyone understood about the force of gravity? Now, this is actually very important. This concept is a little bit important. If you have an aircraft, that aircraft is slowly moving. If that aircraft is slowly pitching, then by measuring the component of gravity, you can find out the pitch angle. So for an example, I give you a very a common example. Say if you have an aircraft, that aircraft takes off. Typically, the aircraft will not have large pitch moment. So it will be at certain pitch angle. And you can find out f of x, f of y, f of z measured by the accelerometer, and then find out the values of theta and phi. So you can find out the value of theta and value of phi based on accelerometer measurement. Unfortunately, you do not have any acceleration measurement in the yaw direction. So you cannot find out the value of yaw from this equation, but you can certainly find out a value of pitch and roll from the acceleration values. So there is a concept which is called as complementary filtering. So what is this complementary filter? Complementary filter, what it does, it combines the roll angle computed by the gyro and the roll angle computed by the accelerometer and adds them together, adding some type of a weighing function. The idea here is, if you think about it, accelerometer will give you the good estimate of pitch or roll when there is not a very significant motion. But the gyro will give you a better estimate when the aircraft is moving fast. So what you do is you adjust the weights to the roll angle computed by the accelerometer, and you add the weight multiplied by the roll angle computed by the gyro and combine them together, and that gives you some type of a complementary filter, and that works very well for the MAV or simple flying robot application. But if you have a very highly dynamic motion, a complementary filter will not work, and you have to go to something called as Kalman filtering. But please understand, these equations can be used to find approximate roll and approximate pitch. Now, let's talk about the aerodynamic forces. So if you look at an airfoil has this particular shape. And what happens because of the shape is you have the regions below the aircraft that have high pressure. So pressure is high. And you have the regions above the aircraft where pressure is low. So because of this uneven pressure distribution, this airfoil is going to experience a vertical force, which is called as the lift. And please understand, the airfoil can only generate lift as long as there is some air velocity. If the airfoil is stationary, it will not generate any lift. And for airfoil, there is always an angle of attack, which is the angle made by airfoil to the incoming air. So if you look at, this is called as the chord. And if you look at this angle is called as angle of attack. And there is a relationship between the angle of attack and the amount of lift and drag that is induced on the aircraft, on the airfoil. As angle of attack increases, you will notice the lift increases. After a certain time, when the angle of attack goes beyond the critical angle of attack, the airfoil stalls, which means that it cannot generate any more lift. It will just generate drag. So critical angle of attack is an important parameter. You don't want to go beyond the critical angle of attack, because that is when the flow separation occurs, which means the flow no longer is attached to the airfoil. Now, there are two ways this can be used. If you look at very highly maneuverable aircraft like F-16 and its variants, what they do is they deliberately disrupt the boundary layer so that there is the selective drag on certain parts of the wing. And the reason for that is that makes the aircraft extremely agile. But for the passenger jets or commercial jets or MAVs that we use, we don't want aircraft to stall. We want to make sure that we are the angle of attack is below the critical angle of attack. So if you look at the force distribution, if I plot angle of attack here, and if you look at the lift force, then you will notice it is something like this. So at critical angle of attack, you get the maximum value of lift. And if the angle of attack increases beyond that critical value, you don't have any lift, and what you have is drag. So again, if you use a computational dynamics tool, CFD tool, you can actually find out the pressure distribution and you can find the force. But for calculations, what we assume is that the resultant of total lift is acting at the quarter chord length. So this is called as the chord of the airfoil. This is the chord from here to here. This is called as the chord of the airfoil, and we assume that the lift force and the drag force are acting at the quarter chord length. Everyone understood this? And the angle made by that chord with the aerodynamic, the air velocity or air speed is called as alpha. Now, there is a concept which is called as the dynamic pressure. So VA is the airspeed. VA is the airspeed or air velocity. Air velocity is the relative velocity of air with respect to the aircraft. When you multiply that by rho and multiply with 1/2, this is something similar to the kinetic energy. So when you take this quantity is called as the dynamic pressure. So this guy is called as dynamic pressure. Once you multiply this dynamic pressure by the surface area S, you get the force, and you multiply that force by this coefficient, which is called as coefficient of lift. Same thing is true with the drag. What you have is, you have the dynamic pressure, which is 1/2 rho VA square. The unit is pressure, and you can see rho is the density. The density is given something like, if you look at this density is given as kg per meter cube multiplied by V square, which is meter square by second square. And as you can see, once I multiply this, I get kg divided by meter second square, and this is the unit of pressure, which is Newton per meter square. So basically, if you look at the dynamic pressure, 1/2 rho VA square, that is nothing but Newton per meter square multiplied by S. S is the area, coefficient of lift is dimensionless, so what you get is the lift force. Same thing happens with the drag force. You have the dynamic pressure multiplied by the surface area multiplied by CD, which is the coefficient of drag. So what you have is CD, which is coefficient of drag. Similarly, you have the moment. This moment again is given as 1/2 rho V square, but please understand that here you have this C that represents the length. So what you have is, you have Cm, which is the coefficient of moment, multiplied by the dynamic pressure, multiplied by the area, multiplied by the chord length, and that you get moment. So lift is given in Newton, drag is given in Newton, and the moment is given in Newton meter. Everyone understood this? Now, one thing I want you to understand is the lift force and drag force. The lift force and drag force are dependent on the air velocity. Lift force and drag force are dependent on air velocity. Can someone tell me the frame in which airspeed or air velocity is described? Stability frame, inertia frame, velocity frame, a vehicle frame, vehicle 1, vehicle 2, body, stability, and wind. So stability frame, IS and JS. So IS, JS, KS is where all these aerodynamic forces are. So can you see VA, which is the air velocity, is expressed in IS, which is in the stability frame. But our forces and moments, those 12 equations, are in the body frame. So what do I need to do? I need to use the transformation to convert the forces in the stability frame back into body frame. Everyone understood this? And for that, I have this transformation matrix. This transformation matrix will take the forces in the stability frame, forces in stability frame, and then convert that into the forces in the body frame. Yes.
So talking about with the transform, as the wing tips off, drops it once past the critical angle of attack, the lift drops off. So some component of lift is related to the angle of attack.
Correct.
Is alpha expressed through that transform there, or does the coefficient of lift
Yeah.
change? Alpha?
Coefficient of lift changes as function of alpha.
Okay.
So, and there is an expression that is coming next. So now one thing I want you to understand is be careful about the sign. So as you can see, the air velocity VA is in the positive direction of IS, but the lift force and the drag force is opposite to KS and IS. That's why you have a negative sign. Because the forces are opposite to the frame. Now, in next few slides, I want to talk about the different aircraft configurations and how the control surfaces change. This is the basic aircraft. And I want to tell you what happens. If you have an aircraft wing, so imagine aircraft, wing here, and if aircraft wants to take off, it needs to generate more lift. So basically what happens is the wings kind of go like this. So the first aircraft that was built by Wright brothers, they had warping wings. So basically they actually rotated the wings. Now what we do is, instead of rotating the wings, we have the part of the wing which is called as aileron or rudder or elevator, we kind of rotate. So whenever you have the control surface pointing down, remember that the lift on that control surface is increased. So if you look at this, let's talk about this. This is called as the elevator. This is the primary means to generate the lift. So basically, increase the pitch. If this elevator pitches down, so basically the aircraft goes up. Similarly, if you look at the aileron, which is aileron here, this is the aileron. Depending upon which direction the aileron tilts, the amount of lift can be changed, and that will allow the control of the roll motion. Then what you have is you have something called as the rudder. So this rudder can actually go left or right, and that will change the basically the lift or the drag or the forces onto this rudder, and that will control the yaw. So this is called as aileron. So this is called as the aileron. This can change the roll. This is the elevator. This can change the pitch. And what you have is, this is the rudder that will change the yaw. So you can, if you have a conventional aircraft wherein you have a prop in the front. So there are two configurations of the aircraft. One is called as the pusher aircraft and other called as the puller aircraft. So if you look at this aircraft, the prop is in front. So it's like a puller aircraft. This is called as the puller configuration because the prop is in front. You can have a prop in the back. You can have the motor and the propeller in the back, and that is called as the pusher configuration. There are advantages and disadvantages for each configuration, but at the end of the day, whether it's a puller configuration or pusher configuration, is going to generate thrust onto the aircraft. And these three are the standard control surfaces for an aircraft. So you have ailerons, ailerons control the roll, you have elevators, elevators control the pitch, and then the rudder that controls the yaw. So roll, pitch, and yaw.
So
Yeah.
in previous slide, VA, capital VA is not the direction of the air itself. Like that's a virtual air that we are computing based on the lift and the drag that we are facing. Am I right?
VA.
Yeah.
So in terms of fluid mechanics, it doesn't matter whether the boat is stationary and the fluid is moving, or fluid is stationary or boat is moving. So this is just matter of reference. So what this is saying is this wing, which is attached to the aircraft, is going forward because of the thrust. So that's why what you have is you have so air is going fast and the airfoil is going forward. So what this is showing the velocity of the airfoil with respect to incoming air. But incoming air is the velocity. Does it make sense? So
Yeah, basically
Yeah.
based on the force that it is exerting, we are
Correct.
kind of thinking that
so this is
because of VA component of the entire velocity of air is only creating a third force on the system.
now when we are trying to draw the free body, this is the free body diagram. When we are trying to draw free body diagram, we only consider the reaction forces. We do not draw the free body diagram on the action forces. So basically, this is the reaction force acting on the airfoil. So because the air is moving, airfoil is moving forward, air is passing the airfoil, that is generating the lift and the drag. These are the reactions on the airfoil. Any other questions? Yes.
It's also supposed to be that the work is at the center.
What?
This is, when we have to, this is assuming that the center mass and center left at the same location.
Okay, so typically, if you do the computational fluid dynamics approach, you will see a very complex distribution. But for analysis purposes, what we assume is that the lift and the drag force, the resultant lift and the resultant drag force are acting at the quarter chord, which is the shown over. You can think about it like the centroid of the airfoil, but it is assumed to be actually at the quarter chord. It is not exactly at the centroid, but it's at the quarter chord. Because if you look at the shape of the airfoil, you can clearly see that if I were to draw the CG, it will be a little bit above the quarter chord length. So, but that is how it is assumed. Any other questions? Okay, so these are the control surfaces of the conventional aircraft. And again, the elevator and the rudder control surfaces deflection is very common. So as you can see, this elevator going down is the positive deflection. This rudder going towards right or going towards left, depending upon how you look at it, is positive. And for the ailerons, please understand, you have ailerons that are flipping up and you have ailerons that are flipping down. They are represented as the overall deflection of the aileron. So delta A is the overall deflection of the aileron. And please understand what makes positive or negative. Now, I want you to understand that a positive sign indicates that the roll, pitch, and yaw is going to be positive. So if the deflection of the control surfaces result into respective positive angle of roll, positive angle of pitch, and positive angle of yaw, that deflection is considered as positive. This is just a typical convention. Now, next is we have something called as the V tail, and this aircraft is not, it's probably not very clear, but what I mean by that V tail is, have you seen an aircraft which is something like this? I mean, if you have seen the movie Top Gun 2, the aircraft that Maverick flies is a V tail aircraft. What? Yes. Oh, no, oh, there is an aircraft front. So if you look at this aircraft is like this, and there is this tail here, there is this tail here, and so basically you have wing like this. So that's why it is called as V tail. And what happens is you have flaps on these V tails, and those flaps can move together or they can move apart. So depending on, so what you have is you have the ailerons which are similar to the conventional aircraft, but you have combined the two control surfaces like elevator and rudder. Elevator is for lifting, rudder is for rotating. So you have combined the elevator and rudder. So what you have is you have something called as the rudder elevator. And how does this rudder and elevator work? So for that, I want you to look at this. So when both the flaps of the V, so you have this V, when both the flaps of the V go in the same direction, when they go in the same direction, what you have is you have the effect same as elevator. When these two flaps go in opposite direction, you have the effect of the rudder. So this is the elevator and this is rudder. So when these V tail control surfaces, they are in sync, then what you have is they act as the elevator. If they are out of sync, then they act as the rudder. And aileron, they control the roll. So ailerons control the roll, and rudder elevator control the pitch and yaw. Everyone understood this? Yeah.
Doesn't it have this component in the roll direction?
Doesn't what?
So this combine this structure,
Uh-huh.
this rudder, it would have some component in the roll direction also, right?
So roll direction is taken care by aileron.
This doesn't have any effect in the roll direction, the rudder.
Actually, let me put it this way. Whenever you have a deflection of the control surfaces, the aerodynamic forces are actually coupled. So there will be some effect, but majority of the roll control is done by the ailerons. Because if you look at an aircraft structure, the aerodynamic interactions are very complex. You have some elevator deflection. That elevator deflection changes the flow around the airfoil, and basically that may give you some desired or undesired roll or pitch. But when we look at the control surfaces, these control surfaces are primarily responsible for those motions. So ailerons are responsible for rolls. Rudder elevators, when they are in sync, act as an elevator. They are out of sync, they act as a rudder. Everyone understood this?
What is the term delta E?
Delta E is delta E. Where is delta E? Oh, delta E is the deflection of the elevator. So elevator deflection. And this is rudder deflection. So I want you to think about it. Can you see this delta E here? We don't have a separate rudder. This is the rudder. and this is the elevator. We do not have separate rudders and elevators. Those two are combined. So that's why this is the elevator deflection is related to the deflection of a rudder elevator on the left and right. Rudder deflection is related to the rudder elevator deflection on the left and right. Everyone understood this? Okay, now this is the flying wing. Now this is again, this is called as the Zagi aircraft. So as you can see, this aircraft does not have a rudder. What it has is it has elevons. And what they do is these elevons, they are used to control the elevator and rudder. However, there are something called as winglets. So you see these things, they are for the lateral stability. If you fly Allegiant Air or Airbus 380, you will see that, or even Boeing, you will see that at the tip of the wing is deflected upwards. That is called as winglet. That deflection is for reason that improves the lateral stability of the aircraft. In Zagi type of aircraft, or in this is also called as flying wing type of aircraft. Please understand, this does not have a rudder. So there is no explicit control surface that will ensure the lateral stability. So that's why we have these winglets. Now the next question is, how do you ensure roll? So you have, how do you ensure yaw? This type of aircraft is very bad in yawing because it does not have rudder. So what happens is you actually utilize the roll to yaw coupling to turn the aircraft. So what you do is you roll the aircraft, and as the aircraft is rolled, basically it kind of yaws. So what you do is to fly this aircraft, you have to utilize roll to yaw coupling, and basically that aircraft would take turn. These types of aircrafts, again, as you can see, it's very simple construction. Control surfaces are easy. And one tidbit here is the first UAV that was built in ASU was built in our lab in 2008. In 2008, we built the first UAV, and that UAV was on this Zagi platform. So at that time, we used the autopilot called Paparazzi. Pickhawk was not there. I was involved in the development of Ardu Pilot. It's an Arduino based autopilot by DIY drones. So I was involved in that, but we used something called as Pickhawk, and this was the type of UAV that built, because this is quite robust. It's very easy. It's quite robust, and it's easy in terms of flying or in terms of stability characteristics. So this is called as the flying wing. In flying wing, you do not have rudder, you do not have elevator, you do not have separate ailerons. So what you have is you have ailerons. Ailerons are combination of elevators and ailerons. Elevators and ailerons. So basically, when these ailerons are in sync, they give you elevator. When these ailerons are out of sync, they give you ailerons. So these are left ailerons and right ailerons. So that is how you can actually fly the aircraft. Now, next part, there's a question. Yes, this is the same thing as B-2 bomber. That is correct. Now, the next part is the aircraft dynamics. So we are going to talk about aircraft dynamics in the longitudinal direction, and we are going to talk about the aircraft dynamics in the lateral direction. In the longitudinal direction, what you have is you are looking at the motion in the I and K plane. So basically up and down, and the motion is the pitching moment. In the lateral direction, you are going to look at the sideways motion, and then you are going to look at roll and yaw. So we are going to look at the aircraft dynamics first in the longitudinal direction, and then next we are going to look at in the lateral direction. So the longitudinal direction is the sagittal plane, which is also called as the pitch plane. So if you look at the aircraft, if you have this aircraft, I'm gonna consider a plane in here. And I'm going to study the motion of the aircraft in I and K plane. And here I would be looking at the effect of force because of the lift force, drag force, and movement. So I would be looking at the lift force, I would be looking at the drag force, and then I would be looking at the moment. So FL, FD, and M. Now, this dynamics is heavily influenced, as you can see, by angle of attack. So if you look at the force because of the lift, dynamic pressure multiplied by the area multiplied by the coefficient of lift. This coefficient of lift is dependent on the angle of attack, elevator deflection, and the pitching moment. So this coefficient of lift is function of angle of attack, pitching moment, and elevator deflection. And I just want to tell you, don't get intimidated by all these terms. The way we do it is, once we derive these big expressions, there is a design data book for each aircraft. For each aircraft, all these coefficients are given to us. So when we are programming, it's actually very simple. There is a standard file format wherein all this aircraft data is available. You write the code in MATLAB or in Python, you actually go read that file and basically populate all these aerodynamic coefficients for that particular aircraft. So you have coefficient of lift, coefficient of drag again is dependent on angle of attack, pitch moment, elevator deflection, and coefficient of moment is again dependent on angle of attack, pitching moment, and elevator deflection. Now, what we need to do is, if you look at the aerodynamics, there is steady aerodynamics, there is unsteady aerodynamics, there is hypersonics, which means depending upon how fast the aircraft is going, the forces actually changes. I want to give you a very simple example and why this topic is very, very important. And you can do your entire PhD or spend your entire career just studying aerodynamics. But what I want to do is I want to give you an intuitive feeling for aerodynamics. I want you to think about an air that is going through a divergent convergent nozzle. So this is divergent, convergent nozzle. Now what happens is you have some airflow going in, some airflow going out. Even though air is compressible, for the sake of discussion, let's imagine air is something like a liquid. which means the density or the mass is constant. So what's going to happen is, since the area here is more, area here is less, we are pushing the same amount of mass. You agree with me? Velocity at exit will be greater than velocity at entry. You agree with me? Same mass is going, mass flow rate is same. Area multiplied by the velocity gives you volumetric flow rate, which is same because we are assuming density is approximately same. What that means is the exit velocity is same as the inlet velocity. I mean, exit velocity is greater than the inlet velocity. Do you agree with me? Now let's think about it a bit. Velocity at inlet is less than the velocity of exit, which means the kinetic energy at exit is greater than the kinetic energy at inlet. Do you agree with me? For conservation of energy, total energy is going to remain constant. So what it means is, in fluids, you have three types of energies. You have a pressure energy, you have potential energy, and you have kinetic energy. Pressure energy, potential energy, and kinetic energy. Please understand that this nozzle is at the same level. This nozzle is at the same level, which means the potential energy is going to remain the same at inlet and exit. You agree with me? The potential energy at inlet and potential energy at exit is going to remain the same. However, pressure energy at inlet will be greater and pressure energy at exit will be less. Do you agree with me? Because total energy is summation of potential energy, kinetic energy, and pressure energy. If the kinetic energy is dropping down, clearly the pressure energy has to go up. If the kinetic energy is going up, clearly the pressure energy needs to drop down. Everyone understood this? This logic is valid when the flow is subsonic. I want to give an example. Have you seen the rocket engines? Have you seen that rocket engines are like this? The flow that is coming through the nozzle, they do not have the diverging converging nozzle. They have converging and diverging nozzle. Why? Because the flow, as soon as the flow crosses the sonic range, which means it crosses the sound barrier, it crosses the speed of sound, this logic that we talked about is no longer valid. And I want you to think about something like this. Air becomes so dense when the speed exceeds the sonic velocity, which means when it goes Mach 1, Mach 2, that air is sort of becoming like a solid sludge. And in that case, think about that sludge being pushed. Now, visualize if you have a sludge, okay? If you have sludge, and if you push sludge, that sort of highly compacted sludge through here, that immediately expands over here, which means you have increase in the velocity when the supersonic flow goes from convergent end of the nozzle to the divergent end of the nozzle. This is extremely important. So the thing that I've shown over here on the top, which is like you have a divergent, convergent nozzle, and then variation in the kinetic and potential energy, that is all valid when the flow is subsonic. When the flow is supersonic, I want you to visualize that air becomes like a sludge. It becomes like a compacted mass. And if you push that compacted air through this converging, diverging nozzle, when air reaches the diverging part, it expands, and that gives the higher velocity. So the logic that we talked about for converging diverging nozzle does not hold true when the flow changes from super subsonic to supersonic. That's why when you look at the design of hypersonic missiles or hypersonic aircraft, they do not follow the principles that we talked about here. So the equations that you see here, they are valid for very low Mach number. For as soon as you go up to 1 Mach or go beyond 1 Mach or go in the supersonic region, the equations that you see are no longer valid. Okay, so what I want you to do is, I want you to understand the total lift is function of alpha, Q, and delta E. So what I'm going to do is, I want to take the derivative of CL with respect to those parameters. So we are going to use Taylor series expansion. Remember Taylor series expansion from robotics 1? So this quantity CL is function of 3 terms. So what I'm going to do is, I'm going to take the derivative of CL with respect to alpha multiplied by the value of alpha, derivative of CL with respect to the pitching moment Q multiplied by the value of Q, CL with respect to elevator deflection, and multiply that by the elevator deflection. So this is the first order approximation or Taylor series approximation. And this approximation works very well for MAVs or small scale UAVs. And what you do is, you have this the first coefficient of the Taylor series CL, which is the constant in the Taylor series expansion. So you write down the expression of lift as the function in the Taylor series first order expansion, and the only difference is you want it to be dimensionless. You want it to be dimensionless. So there is a customary that we divide it by VA. So this Q is in Newton meter. So we need to divide by this VA, meters per second, just to maintain the dimensional compatibility. Otherwise, please understand that one term is in terms of forces, other term in terms of forces, but just to be consistent, we have to divide by VA. Now, this is the linear aerodynamic model that we are going to use, just like the force due to lift, force because of drag, and movement. You have a linear aerodynamic model that is dependent on the angle of attack alpha, pitching moment Q, and the elevator angle delta. And please note that these coefficients CL naught, CL alpha, CLQ, CL delta E, they are defined for each aircraft. So as soon as you select an airframe, you will have a design data. There will be a design data file that you can import inside MATLAB, wherein all these coefficients are given to you, and you can use those in your simulation. Now, one thing I want to talk about is, why does an airfoil stall? So the stalling of an airfoil is a very important concept. So as long as the flow is laminar and the flow is attached to the airfoil, everything is good. But what happens is, at certain angle of alpha, which is angle of attack, certain angle of alpha, the flow that is coming past the airfoil starts separating. And then what happens is, you get these eddies that get formed. And as soon as you have eddy formation, that causes the flow to separate, and you no longer have the lift. So if you look at the aircrafts, for example, bombers, B-2, what they have is on the airfoil, on the wing, they have small projections that minimize the flow separation or delay the onset of flow separation. But flow separation is the primary reason for stalling of an airfoil. If you look at the nonlinear lift model, this is how the nonlinear lift model looks like. So you have this angle of alpha, and as angle of alpha is increased, the lift increases, and at certain point, this kind of drops down. And please understand, it is very difficult for us to understand or draw this. So most of the times, what we do is we do wind tunnel experiments, or we perform computational fluid dynamics to get this coefficient of lift versus alpha relationship. If you were to look at a flat plate model, so imagine you don't have airfoil, but if you have a flat plate, you can actually derive the lift expression in sort of a closed form. So the equation that is given here, 2 sine square alpha cosine alpha, is the flat plate assumption of the airfoil. If that airfoil, rather than being something like this, if it's a flat plate, it will show you the lift pattern, something like this. But for UAVs or MAVs that we are going to study, we are going to work in the linear region of the lift model. Now, but if you study exotic aircraft, typically the exotic aircraft or the aircraft that fly at a high Mach number, or they are bigger, they always use a linear and nonlinear model. And what you have is, you have sort of a blending function that blends the linear model and the nonlinear model. So we are not going to use this, but if you have to perform the real life simulation, then what you will do is you will use this linear model and nonlinear model and use a blending function that will combine these two. Okay, I'm going to stop here, and I would be happy to answer any questions that you may have. But one important resource which I would like to show you is something like MATLAB aircraft simulation. So I have been asked by students, undergraduates and graduates, how do we get an A in this course? So what I'm going to do is, I'm going to give some additional assignments that would allow you to score, and that way you would be able to get an A+ or push your grade in this course. So what I'm gonna do is, there is this webinar, which is the flight control simulation and design of an aircraft. And along with that, there are some very nice MATLAB simulations that you can run for a fixed wing aircraft. I'm going to assign some of these webinars and associated activities as bonus activities, so that if you score above 120, you will get an A+. So I'm going to give some additional assignments, because a lot of students came to me and asked me, hey, how do I improve my grade? Yeah, I know you don't have an A+, but how do I get an A+? So just for that, again, these are purely optional. You don't have to do those, but I would strongly recommend, if you want to further your understanding of UAVs and understand how actually you can program inside the MATLAB and do some simulations or the actual hardware, I would recommend you doing these webinars. Yeah.
Will this be like put as a link in your Google?
Yeah, I'm going to assign, once I cover force and movement, I will assign that in the canvas.
So for passenger aircraft, how are they finding the different craft? Like,
So-
can we downsize the entire system and try wind tunnel experiment and find it? Then, for example, the value for will that work?
Yes. So actually I spent a lot of time in my life doing this. There is something called as dimensional analysis. What is dimensional analysis? Say for example, if you want to build an aircraft, it is not possible to build an aircraft, put it inside the wind tunnel and perform the actual testing. So what you do is you build a small scale version of the aircraft. But you have to maintain similarities. There are three types of similarity. One is called as the geometric similarity, which means the dimensions need to be proportional. Then you have to maintain something called as the kinematic similarity, which means the kinematics of the large scale aircraft, the small scale aircraft is similar. And then you have to maintain the dynamic similarity, which means the forces and the movements on the large aircraft and small aircraft, they are same. A classic example is Reynolds number. If you want to study an aircraft, what you do is you will fly the small aircraft at the same Reynolds number as the large aircraft to maintain a similarity. But maintaining kinematic, dynamic, and dimensional similarity is not sufficient. What you have to do is you have to actually perform something called as dimensional analysis. Dimensional analysis is matching the features of the large scale model with the small scale model. So there is a, I would, if you are really interested in this, there is a big thick book on dimensional analysis and dimensional similarity. So that will show you how you can build small models, test those small models, and reasonably accurately predict the performance of large scale systems. It's a very fascinating area, because many a times, for example, I give you an example. Shuttle, so space shuttle, you're not going to build tens of space shuttle, you're just going to build one. But to build that, you need to understand what are the forces and what are the movements. How do you extrapolate? There is no linear extrapolation. As a matter of fact, there is no non-linear extrapolation. It's a very complex process. So just look it up at dimensional analysis. And I spent a lot of my time doing that when I was a graduate student. So I'm gonna stop here.